Thanks for coming to the afternoon session. So we're going to start with the first talk on deep generative models for molecular simulations, and this is by Professor Jose-Miguel Hernández-Lobato. He's a professor of machine learning in the Department of Engineering at the University of Cambridge, and he also is the director for the Cambridge ELLIS unit. So remember that this event is organized by ELLIS. So we're very happy to have a fellow ELLIS member from another unit giving this tutorial, this lecture. Thank you for coming.
Good. Great. Yeah, thanks a lot for inviting me. And I'm very happy to talk today about some of the work that I have been doing in my group in this area of generative models for molecular simulation. And I'm going to give this as a brief tutorial, an introduction to some of the methods that we can use to simulate molecules, and then how we can improve over them using generative models. So let's start with some introduction and motivation for what we are going to be doing. Our goal in this tutorial is going to be to model this Boltzmann distribution of molecules. Okay? This is a probability distribution here that receives as input the 3D configuration of the atoms of a molecule. Molecules are not rigid objects. They're going to be flexible, and they're going to be vibrating and moving. And we're interested in capturing these movements. And the molecules that are going to move and to be found in different configurations with this probability. And the probability has this function here that is called the energy. So the probability is going to be exponential minus the energy, and there are going to be some scaling constants there. And molecules are going to prefer configurations of low energy. This is all common knowledge from physics. So we can imagine that someone gives us access to these energy functions. They are going to be models based on physics. Someone builds a model based on physics that describes how the energy of molecules behaves. And then based on that, we assume that we are going to be able to draw samples from this distribution. And working with these distributions is going to be important because they allow us to answer very relevant questions. Like, for example, if a drug-like molecule is going to bind to a target protein or not. And this is going to be very relevant in drug design, drug discovery. Maybe you're also interested in new materials for specific problems, and you want to simulate molecules. I have an example animation in this tab. This is a website from a company that is called D-Shore Research. And they build a specific hardware to do simulations of molecules. They build supercomputers that are going to be doing these simulations. And we have an example of a simulation in this animation. You have like a big molecule, a protein or so, formed by many different atoms. And it's shown in kind of this whitish color. And then you have a drug-like molecule that is kind of interacting around. And at some point, it finds like a binding spot here. Okay? So this is a simulation of the molecules, and ideally we want to obtain these simulations because they can be very useful to know what's going to happen without actually doing experiments and measuring things in a laboratory. Okay? Good. So we are interested in doing these simulations, and the question is, how do you do those simulations? We are interested in generating samples from this Boltzmann distribution for the 3D configuration of the atoms of molecules. Okay? And the obvious technique that we could use for this is a Markov chain Monte Carlo. Okay? Markov chain Monte Carlo is going to allow us to generate samples from a target distribution. We are going to call it a P star. And this is going to be our Boltzmann distribution. We can evaluate it by calling our physics-based model that gives us the energy and potentially the gradients of the energy as well. Okay? Markov chain Monte Carlo methods will use this target distribution to construct a transition operator that is going to be a distribution, a conditional distribution that, given the previous state of my Markov chain, it gives me the next state. And this transition operator has the property that asymptotically, the samples that it's going to generate come from the target distribution, from our Boltzmann distribution. And this is illustrated in this example here. You have a Markov chain that starts in this region. Is this sequence of points in green? And we are targeting just a simple Gaussian distribution in this case. So the samples generated by the Markov chain Monte Carlo method are correlated. They satisfy this Markov property that the next sample is just generated as a function of the previous one. So because they are correlated, to generate accurate samples, in the end I will need to generate a very large number of samples, okay, so that I can explore the whole target. Who is familiar with Markov chain Monte Carlo methods? Who has seen this before? Okay, some people have seen this. I'm going to go a bit quickly on this. Obviously, the question is how do you get this Markov chain Monte Carlo, the transition operator for a Markov chain Monte Carlo method? You are given a particular distribution. How do you guarantee that you generate samples from a target asymptotically by using a transition operator like this one? And you can guarantee that your transition operator will generate samples from the target if it satisfies this property called detailed balance. Detailed balance means that the probability of sampling one position x from the target and then moving from x to x prime using my transition operator is the same as having sampled x prime from the target and then moving from x prime to x using my transition operator. That's why this thing is called detailed balance, it means that if I am sampling from the target distribution, the probability of moving from one point to another is the same as moving in the reverse direction, okay? And you can show very easily that if your transition operator satisfies detailed balance, you will keep the target distribution invariant, okay? That means that if you have a data point sampled from the target, you are guaranteed that the next data point is going to be also sampled from the target. And you can do it very easily. If I am sampling from the target x, and then I am moving to x prime, what is the marginal distribution of x prime? I only have to sum out x to get that marginal distribution. And because my transition operator satisfies detailed balance, I know that this thing, I can basically swap and write it instead of p star x, I can write it as p star x prime, and then here I have the transition operator reversed. So I write now px prime instead of px, and I write now the transition operator in the opposite direction. And then the sum over x now is only over my transition operator, which is a distribution, okay? And that means that the marginal for x prime is just going to be the target distribution, which is what I wanted. So my transition operator, if it satisfies detailed balance, is going to leave my target invariant, okay? So now why I'm telling you about this? Because the way to construct transition operators is going to be to ensure that they satisfy detailed balance. If you want a transition operator that samples from a target, if the transition operator satisfies detailed balance with respect to that target, it's guaranteed to sample asymptotically from that target. And that's what we are going to obtain in practice. In particular, there is this algorithm called Metropolis-Hastings, which is the most successful, or probably the most important algorithm in engineering. It has tons of applications, and it allows you to sample from a target distribution by just creating a Markov chain transition operator that satisfies detailed balance with respect to this target. Who has seen Metropolis-Hastings before? Okay, some people have. Good. So Metropolis-Hastings is actually a very simple algorithm, and it's basically involving only these 3 steps. To construct your transition operator, you do as follows. You are at a current state x, and you are going to sample a proposal x prime from this proposal distribution Q, okay? And most often, this is going to be a Gaussian centered at the previous value. So you have a Gaussian centered at the previous value x, and you add a bit of Gaussian noise to the previous value x, and you get the new data point x prime. And x prime is your proposal. It's not really what is sampled from your transition operator. This is not what your transition operator is sampling. It's just a proposal. And now we're going to accept or reject this proposal with this probability, which is the minimum of 1. And then here we have this ratio between the target and the product of the target and my transition operator evaluated at x and x prime, or changing x and x prime. Okay? And then if I accept, it means that the output of my transition operator is x prime. But if I reject, the output of my transition operator is just x. Okay? Which means that my transition operator, the sample that it generates, is just the previous state. This is the most common bug when you code Metropolis Hastings. A lot of people may code Metropolis Hastings. They implement it. Oh, it's not working. Why it doesn't work? Because when you reject, you need to duplicate the previous state. Your next state is just the previous one when you reject. And when you accept, your next state is just going to be the proposal x prime. Good. Any questions on this? No? Good. So the good news of Metropolis Hastings is that it works even if your target is not normalized, which is going to be our case. Okay? Our target is exponential of minus the energy, and I don't know the normalization constant of my target. So I can use this method to draw approximate samples from the target. And you can very easily show that Metropolis Hastings satisfies detailed balance by just using the definition of the transition operator. So if you sample x from the target and you move at x prime, the probability of moving from x to x prime, all this, you can write it in terms of the probability that you move to x prime using your transition operator, and this is the probability that you sample x prime from x using Q, your proposal, and then the probability that you accept, which is the minimum of this ratio. And the product of this thing that is positive times this minimum is just I can get the product inside of the minimum operator. And then what is going to happen is that I have what I am multiplying here instead of 1. And here now that I had, instead of the ratio, I remove the denominator. Because what I am multiplying for, I am multiplying with this thing, and it's the same as the denominator here, so it cancels. And now what I can do is take this term out of the minimum as a product, which is what I am doing here. And this is precisely now the probability of having sampled P star from the target, and then applying the Metropolis Hastings transition operator. So very easily to show that Metropolis Hastings satisfies detailed balance. Good. Now, some questions. Yes, one question.
A very basic question. I didn't get, is it the x or x prime, the energy level that you want to predict? What do you want to predict?
Okay, what is x and what is x prime? We are interested in sampling configurations of molecules. And these are 3D configurations of molecules. So x and x prime are going to be the 3D coordinates of atoms in space. And when we draw samples, imagine that you draw a few samples. That will give you a snapshot of possible likely configurations of the atoms in space. It's going to tell you more or less what states the atoms could be found in practice.
The structure of the atom?
It will be the 3D configuration of the atoms. So let's keep it simple. And you could have just a 2D-dimensional space, x1 and x2, and maybe you have one atom in this position. Okay, so you have some coordinates here. Maybe one sample is this point, but maybe another sample could have been maybe like this one. okay? So it would be like these coordinates. They are just the spatial coordinates, okay? You could imagine the way people run these simulations is that they define a box, and then they put the molecules inside of the box, and they say how are the molecules going to move within the box, for example. And your coordinates will be maybe relative to the borders of the box.
There are vectors, x and x prime are a vector of the location of the atoms?
They are exactly the locations of the atoms. They are exactly the locations. Good. Good. Some question. This sounds great. Metropolis Hastings allows you to sample from a target. Have we solved the problem? Do you think we have solved the problem with this algorithm? Any volunteer? What can go wrong when you apply this algorithm? Anyone wants to say something? Yes?
You can get stuck in very large dimensions.
You can get stuck?
So if your distribution is large dimensional, you can get stuck into some sampling similar conformations.
That's right. So you could have, it's not really high dimensional, but you could have very complicated distributions. Your distributions could be, for example, multimodal. You could have a mode here, and maybe there is a low energy barrier, and you could have another mode here. And you may initialize your Metropolis Hastings algorithm, and you start drawing samples from here. But then the probability that you move to this region could be very low, because Metropolis Hastings is going to calculate this ratio. And if you propose a state here, then you are going to reject, and you won't move. So you will have problems exploring. Yes?
Do you necessarily need two bounds? Because what if you have like one, but you're in very large dimensions, let's say?
What do you mean by bounds?
Sorry, you said like one modality.
Oh, yeah, there could be many modes. And
I'm saying something simpler. What if you have like one modality, but you are in very, very large dimensions?
yeah, that should be. So there could be problems there, but we are going to see a method that avoids these problems, and that works better. So in high dimensions, we're going to see some examples of. I'm not fully sure if that could be a problematic. My impression is that it's probably fine. It depends on you could have a very high dimensional distribution, but if it is smooth, maybe this thing is going to work fine. The problem could be, for example, if you have distributions that are, for example, if your distribution is like this, quite correlated, Metropolis Hastings is drawing proposals from a spherical Gaussian. Okay, and then you are going to throw maybe a proposal here, you accept it, and then maybe based on this, you need to draw another one like this, and you accept it. And you cannot draw a proposal you cannot use a proposal that is like this, because you will move outside of your target and you will reject. So things will be slow with this method. We are going to see an example here of how it would work. In this case, we have this target in red, and we are drawing samples with a proposal that has Gaussian noise with a small variance. This is a small. And then you see that there are two modes in the target, but we are not really exploring much. If we increase the variance of our noise, and we have a very large variance now in the distribution that draws our proposal, we are going to fall outside of the target, and we will be rejecting. Here you see the rejections here. You are rejecting, 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 and then you are wasting computation, because you are proposing many samples and you reject, okay? And if you use a variance that is slightly intermediate, not very large, not very small, here you are exploring better the target, okay? This shows more or less how this method works. problems, the one we mentioned before. If you have, for example, high correlations, then this method will need a lot of steps to explore the target. So if you have a highly correlated target, like this one, then you need to have a small noise in your proposal, otherwise you fall outside of the target. And the time that it takes you to explore the whole target will be very large. There is a very simple modification that can make Metropolis Hastings much better. And this is the Hamiltonian Monte Carlo method, which is based on Hamiltonian dynamics. And the idea is that instead of using this Gaussian proposal, which is not very efficient, you just do like some random perturbation of your current state. That's not very efficient, okay? It's like just adding noise to your current sample and then see if it is good or not. And maybe sometimes it will be good, but maybe most of the times it's not going to be so good. So Hamiltonian Monte Carlo does a much better job at proposing new states. And it proposes new states by simulating Hamiltonian dynamics. The idea is that we are going to assume that we have a potential energy, which is just our target energy, but then we add some kinetic energy. And then we have the Hamiltonian, which is just the sum of these two energies. And this is the same as if you multiply together two distributions. The energies are related to the log of your distribution. When you sum the energies, it's more or less the same as multiplying together distributions. So here you are adding extra variables, which are velocities, okay? And you assume that they follow a Gaussian distribution. This is a quadratic form for your energy. Exponential of a quadratic is Gaussian. And the idea is that you have now velocity, these variables, you sample them from a Gaussian, and then you just simulate Hamiltonian dynamics. You evolve your state X using Hamiltonian dynamics, okay? And they are reversible, which is going to be useful to satisfy detailed balance, because if you just change the sign of your velocity and you simulate Hamiltonian dynamics, you just go back in time. So this leads to this method called Hamiltonian Monte Carlo, which is probably the best existing method for generating samples. And this is actually the method that is used in practice to do simulations of molecules, okay? The simulation that I showed at the beginning that showed this protein and with the drug-like molecule was done using Hamiltonian Monte Carlo, okay? And the way it works is that you add these Gaussian velocity variables. You are going to start by sampling them from the marginal. It's an exact sample. We can sample from Gaussians. And then what we are going to do is simulate Hamiltonian dynamics for an amount of time. And the Hamiltonian dynamics are going to specify my proposal. So given my current state and my velocity, is going to result, the Hamiltonian dynamics are going to result in a new state and a new velocity, okay? This is reversible. So these two transition operators, not transition operators, but proposals are the same. And in the Metropolis Hastings acceptance probability, I had the ratio between the target and the transition operator, not the transition operator, the proposal distribution. And the ratio between proposals is going to cancel because it's the same. So I only have the ratio between the exponential of minus the energies, minus the Hamiltonian, okay? So I just have now, in my Metropolis Hastings acceptance probability, I'm going to have the ratio between these two things. And one property of Hamiltonian dynamics is that it keeps the energy constant. The total energy is constant. If the total energy is constant, the total probability, the probabilities are constant, and these two things are the same. And this means that the acceptance ratio, when I run Hamiltonian dynamics as my proposal, is 1. I always accept. So I'm never going to be rejected. That is pretty amazing. Now you are going to have a very efficient method. You are going to just propose new states by running Hamiltonian dynamic simulations. And that's it. Obviously, the trick and the caveat is that you cannot simulate Hamiltonian dynamics exactly. You need to do approximations. You are going to use, you will need to do like some discretization. And this means that your energy is not going to be conserved exactly. And the ratio between the energy of the new state and the previous state, this difference between Hamiltonians, is not going to be 0. And this means that sometimes you will be rejecting. But the times that you will be rejecting is going to be small. Good. Any questions on this? No? OK. So yeah, this is a state-of-the-art sampling method. And I'm going to show you now a simple animation illustrating the difference between Metropolis Hastings with a Gaussian proposal, a random walk based on a Gaussian proposal, and Hamiltonian Monte Carlo. This is a video that was done by some member of the machine learning group at Cambridge. I don't know if you know him. His name is David Duveno. He was a PhD student at the time that I was a postdoc there. He's now a professor of, he's a professor at Toronto. He's very well known because he came up with neural ODEs and other fancy models. He also did important contributions in graph neural networks. And this is a simple animation that is based on the Harlem Shake video. I don't know if you remember the Harlem Shake. Who remembers this? It was like a viral video with this song, and people were just, I don't know, making tons of versions of this. It's just this kind of music, and there are two parts in the music. And the idea is that you had maybe some person kind of dancing in the first part of the music, and then the music changed, and then suddenly you had like hundreds of people dancing together. You had many videos that could be similar. So this is the same thing, but now with when you draw samples, and the samples are from these targets that are just the letters of Harlem Shake. Okay, so you have distributions. I think they are probably Gaussians. These are mixtures of Gaussians, and they have like the form of an H, an A, R, and so on. And you want to sample from these distributions. The Markov chain state is illustrated with the red dots. Okay. And we're going to see how the chain is moving because the dots are connected with these yellow lines in the same, the sequence of dots. Okay? And we're going to see how Metropolis Hastings is not very efficient at the beginning. It does these Gaussian proposals that are not that efficient, and then we switch to, when the music changes, we switch to Hamilton Monte Carlo. Instead of getting more people dancing, now we have a much more efficient sampler. Okay? So let's have a look at the video. And we can see now the differences. This was done by David Duveno and Tamara Broderick. Tamara Broderick is now a professor at MIT. Good. So I think the sound should probably work. Here, let's see if this works. So this is Hamilton Metropolis Hastings. And the red points don't move much. Okay? You just do tiny steps. And this is now Hamilton Monte Carlo, and you can see that now the trajectories that you take are way broader. You can move much more in this space. Okay, so that's it. This is in YouTube. If you just search for Hamilton Monte Carlo and Metropolis Hastings, you can just look at it. Do you want to look at it again, or? No? Okay. Good. So that's great. So this is how people draw samples from these Boltzmann distributions. They just run Hamilton Monte Carlo. They run Hamilton Monte Carlo without Metropolis Hastings corrections, because they take very tiny steps, and then Hamilton Monte Carlo is going to accept most of the time. Sometimes it will be rejecting, but they don't even care about the rejections, because the errors introduced by not rejecting when you should, they would be very small. So there are some limitations in these Monte Carlo methods. Okay? First of all, they are stacked into different modes. If you have two modes in your distribution that are far away, separated by these low energy barriers, it's quite unlikely that your sampler jumps to a missing mode, okay? The samples that you generate, we have seen that they are correlated because it's a Markov chain, what you are running. And another important thing, imagine these guys from D-Shore Research. They are using these supercomputers to run these simulations. They spend tons of compute to generate your simulation up to a particular time. And now to generate the next sample in your chain, you forget about all the effort that you spent generating samples in the past, and you just generate a new sample based only on the previous one. You just forget about all the previous samples. And that's extremely inefficient. You spend a lot of compute generating high-quality samples. Why don't you use those high-quality samples to make better samples in the future, okay? So samples from the past are not used to improve the generation of samples in Markov chain Monte Carlo methods. You need these small step sizes to guarantee acceptance. And this means that if you want to simulate physical processes that take a long time, like a protein folding or these drug-like molecules binding, that's going to take you forever when you run these simulations. You just do very tiny, tiny steps, and you just can only simulate very, very small processes in time, okay? So sampling some molecular events could even take years. So the idea is, can we improve on these methods by using generative models? Generative models are very flexible methods. They work by taking some tractable distribution, a Gaussian, for example. You sample from your Gaussian, and now you are going to transform those simple Gaussian samples into something very complicated by making use of a neural network, okay? And the idea is that when you transform your Gaussian through the neural network, you get this approximate distribution Q that is going to be ideally close to your target, okay? And once you have trained your generative model, you draw independent samples. It's not like the Markov chain Monte Carlo method that it generates correlated samples all the time, okay? So once trained, you just generate independent samples. You are going to have some small amount of bias in your generative model, and you may want to control that. We're going to see later on methods that will allow you to eliminate bias in the samples from your generative model, which is pretty impressive. So you can have a model that is going to be approximate. You can make it very, very good by increasing the complexity of your neural network, but you will always have some bias in your model. But we're going to see methods that will allow us to eliminate that bias, okay? So you could see now what could be the future of molecular simulations in the next years. Right now, you probably have seen all this generative AI in social media generating all these fancy videos, all these fancy images. You typically write a prompt. You say, I want a picture of whatever, and then a neural network generates your picture. I want a video of maybe this woman walking in the streets of Tokyo, and you get a fancy video like that. Maybe in the future, in the area of molecular simulations, you are going to have now neural networks that will receive a prompt describing the molecular systems that you want to simulate. That is going to be, for example, a protein with a particular sequence of amino acids, and maybe there is a drug-like molecule, and maybe I have details about the simulation. Maybe I'm going to simulate in a box where I have water molecules, and I have my protein and my drug-like molecule there. There is this temperature, there is this pressure, and I want just a description of states in which my molecules could be. So my prediction is that most likely in the next years or so, we will have simulations of molecules in this way. Good. All sounds great, but there are huge challenges in getting this to work. First of all the generative AI that you have seen in social media is trained based on data. Okay? You have huge data sets of images, huge data sets of videos. You just train the models on that data, and the models generate similar things. With molecules, there is not that much data available. Okay? You have access to energy functions. That's great, but you don't have data. So the way that you will have to train your models is different. So you will require now new ways to train generative models if you want to use them in this setting. You don't train them from data, you train them from energy values. Molecules have a lot of invariances. The molecules, if you translate them in space, if you rotate them, they are the same molecules. And if you want your models to be accurate, they should capture those symmetries and those invariances in molecules. And you will have to incorporate that into your models. There are ways to do it, but it's not straightforward. Your distributions are going to be multimodal. Molecules are not just in a particular state, and that's it. They can be in different states with different probabilities. This means that your Boltzmann distributions, they are going to be highly multimodal. And if you want to feed generative models to those distributions, you will need to be able to capture the different modes. As I said, the models are going to be biased. It doesn't matter how much data or how you train them, there are going to be always approximations. And you will need to do something to remove that bias. You may want to work with large molecules, with proteins that include many, many atoms. This means that your distributions will be high dimensional. You will have to work with the spatial coordinates, the x, y, z coordinates of the atoms of a big molecule. There are many atoms, you have many dimensions. You will need to work in these spaces. Yes?
So can you say a bit more about the first one? You say energy value is not sample, so what would be a sample?
Yeah, a sample is a data set. So when you train a generative model, someone says, oh, you have your data, and you have these data points. You have a total of n data points from some target distribution. You assume that there is this target distribution px star, and you assume that xi is sampled from that distribution. In our case, someone says, oh, this is your energy function. And you can evaluate it at some inputs, and you can get its gradients, but that's it. Okay? And then how do you train a model that is going to generate samples from the corresponding Boltzmann distribution? Okay? Yes?
You're using energy function and probability distribution interchangeably?
Can you repeat energy?
The energy function and probability distribution are interchangeable?
It's the same because the probability distribution is proportional to exponential of minus the energy. So if you have access to the energy, you have access to the unnormalized density.
So you can calculate the likelihood using the...
You will be able to calculate the unnormalized density of the Boltzmann distribution. But you want to know what are likely states, what are likely samples from that distribution. You need samples from the distribution. If you have samples, you can approximate integrals with respect to your distribution expectations. And most of the physical quantities of interest will be expectations with respect to your Boltzmann distribution. Good. Cool. An example application of why these simulations and working with Boltzmann distributions are useful. You may want to estimate the binding energy of a molecule to a target. Is this molecule going to bind to a target? If the energy is low, when the molecule is attached to the target, it's quite likely to bind. Okay? If you're interested in estimating these binding energies, you can estimate them using these simulations. And right now, pharmaceutical companies like AstraZeneca, they're spending tons of compute just running simulations to estimate binding energies of molecules. Okay? They spend a huge amount of money on this. And they are using only these methods based on simulations. It's quite likely that in the future, there could be methods based on generative models that do it much faster at much lower cost. Good. Great. So this was kind of some motivation for some work. I'm going to describe you now some method from my lab trying to train generative models that will generate accurate samples from these Boltzmann distributions. And this is some work that was published at ICLR last year. Okay? It was done with these amazing collaborators. Good. The first thing that we need to choose if we want to use a generative model to approximate our Boltzmann distribution is to choose a particular model. There are tons of models available. You have like from normalizing flows, you have diffusion models, You could have GANs, you could have autoregressive process models, I don't know, like tons of choices. What we are going to focus here on is in using normalizing flows. And the main reason for this is that they are very easy to work with. We want our models to generate samples fast, and we want our models to give us density estimates. We want our model to give us the density of the samples that it generates. And we're going to see later that that can be used to eliminate bias in your model. So in this work, we focused on normalizing flows for that reason. They can generate samples fast. They give you also density estimates of your values. A lot of people are using now diffusion models. Diffusion models are very flexible, but they have some limitations. They are usually slower to sample, and they don't give you densities of the samples. You can, in theory, get densities from a diffusion model, but it's not numerically stable, and it's very computationally expensive to get those. So for us at this stage, it was not an option. I can tell you later on that we are working also on diffusion models for addressing this problem now with new techniques, and I will have some news to mention at the end of the talk about that. But we are going to be using normalizing flows in this work. The way normalizing flows work is as follows. By the way, who is familiar with normalizing flows? Who has seen this before? Okay, a few people, but not that many. Cool. So in a normalizing flow, the idea is that you start, as all generative models, you start by sampling from a tractable distribution like a Gaussian, and now you are going to apply a nonlinear transformation to your samples with the key characteristic that in a normalizing flow, this nonlinear transformation is invertible, and this allows you to calculate the density of the transformed variable using the change of variables formula. So if you start with a tractable sample x from a Gaussian, you can then transform that using this function f to obtain a transformed variable y, and then you can obtain the probability of y as a function of the probability of x, and then this determinant, the absolute value of the determinant of the Jacobian, the determinant of the Jacobian of your transformation. Okay. And obviously, this is going to limit your transformation function because it has to be invertible, and then you want to be able to calculate this determinant of the Jacobian quite fast. Okay? So that's going to introduce a lack of flexibility in normalizing flows. This function f that you use to transform your samples, it has to be a bit simple. But you can just concatenate many of these simple functions, one after the other, to increase flexibility. And then by doing that, you will apply not just one transformation, but you use many, like this one here, and in the end, you get a very complicated target. Okay? And by adding many of these transformations or layers, you can have quite flexible models in the end. Good. So maybe some very simple, maybe some of the basics. You may have this formula. Where does this formula come from? Like, is this kind of magic, or where do you get this log determinant, all of that? What's going on? It's actually very simple. The idea is that when you transform the data using a simple invertible transformation, the probability mass is going to be preserved. This means that if you sample let me see. If you sample in a very tiny interval, this would be like a differential of x. Okay. The probability of sampling here, maybe it's going to be p of the probability of having something in this interval is probability of x differential of x. Okay. It's just the density at that interval and times the width of my interval. It's super small, so it's a differential of x, and then that's going to be mapped into another interval here, okay? And this is going to be now very tiny, and it's going to have some density, p of y, okay? And what happens is that the probability mass is preserved. The probability of finding my variable x in this tiny interval is going to be the same as the probability of finding my variable y in this tiny interval, and I just have this equality here. So now I have a way to solve for the probability of y as a function of the probability of x. It's just the probability of x, differential of x, and then differential of y. Okay? And differential of x, differential of y is just a derivative. Okay? You need to still add an absolute value. And the reason for this is that the way you transform the data could be you could reverse the location. So the transformation could be invertible, but maybe it's changing the order of the variables. So I have this x here, and it's mapped to this point, but then x plus some variable is mapped to a smaller value. So the transformation is maybe not preserving the order. It's still invertible. And if I want to avoid problems, then I have to add this absolute value, because otherwise here I will have like a negative thing, and you cannot get negative densities. Good. This is in one dimension. In higher dimensions, it's more or less the same stuff, but instead of mapping now tiny intervals like this one into other tiny intervals, now you are mapping tiny volumes into other tiny volumes through these transformations. And this other volume, this is a parallelogram, and you have the formula for the volume of the parallelogram, and it's just a determinant. Okay? A determinant, and then the coordinates of the parallelogram is given by the derivatives, and that's basically where you get this formula. I won't go much into the details of this. You can, if you are curious, you can look at it on your own. But that's basically how you change the density of variables through transformations. And this is basically how normalizing flows work. Good. Any questions on this so far? No? Good. So the question is then, how do you implement these transformations in normalizing flows? What transformations you use? It turns out that obviously you want flexible transformations, but transformations that can calculate these determinants of the Jacobians very efficiently. And one method that works very well and is very flexible is based on this concept of coupling layer. And the idea is that you do a nonlinear transformation of the variables in the following way. You are going to take your input variables x, and you are going to split them in two parts, some right part and a left part. And now the right part is not transformed. Okay? It just passes without any transformation. So there is here no change to the right part of my variable. And then the left part here, it goes through a nonlinear transformation that depends on the on the right part. So there is a neural network that specifies my transformation. It's applied independently to each dimension, but it generates a new value. And when you look at the Jacobian of this transformation, what is going to happen is that if I have a matrix here, I can divide it maybe in right and the left part. This would be right and left. Okay? And the right part is not transformed. Okay? So the Jacobian is going to be 1. The variables that you generate at the output is the same as the input. The derivative of that is 1. And it's going to be diagonal because each variable does not depend on the other ones. So the Jacobian is going to have a diagonal here that is all 1s for the right part. Okay? And now the left part is going to depend, obviously, its dimension is transformed as a function of that dimension, but also depends on all the other variables on the right, okay? Because you take these right variables, you feed them into a neural network, and this neural network tells you now how to transform each of the dimensions in x left. So x left is going to depend on its own, so I'm going to have non-zero entries in this diagonal here, But now it's going to depend also on the right. So all these entries in my Jacobian are also non-zero. And this is 0, this is 0, this is 0, this is 0, this is 0. And what is the determinant of this matrix? Any idea? Yes? No. Yes? It's going to be the product of the entries in the diagonal. Okay? It's a lower triangular matrix. The determinant of the matrix is going to be the product of the elements in the diagonal. So even though this matrix could be quite large, I can calculate its determinant very fast. I only need to look at the elements in the diagonal. Okay? So that's why you can use this. I mean, these transformations are quite used in normalizing flows. They are called coupling. And here we use something called neural spline flows, where this transformation is given by a spline for each dimension. Each dimension has some input x here. The transformation is determined through these nodes, the black points, and some derivatives at the points. And it's specified to be monotonically increasing, so it's invertible. And it turns out that because you work with splines, which are just polynomials of degree 3, you can obtain the inverse analytically very fast. And you see the inverse function is shown here in orange. You obtain it super fast because you have an analytic solution for the inverse. So what you have is now a neural network that receives the right part of the variables, and it outputs the location of these nodes in black, and it gives you some derivative values. And given that, you obtain the inverse right away. And yeah, this is like a very, very flexible transformation. And by adding several of these layers, you get like a very flexible model. This is the transformation, and the density. If you imagine that you have a uniform density, then what you are going to, the density of the transformed variables is the product of the base density and this transformation, the derivative of this transformation. And you have here the derivative. The transformation is cubic polynomials, and the derivative of a cubic polynomial is a quadratic function, and you can see the quadratic functions here. All these are quadratic functions. This is like a parabola here. Okay. This is also a parabola. These are all quadratic functions. But it can be quite flexible, the transformation. Any questions on these coupling flows with splines? No? Good. So this is basically the model that we're going to be using. And now the next step is how to make our models invariant. Molecules are invariant to rotations and translations. How do you incorporate those invariances into these models? Anyone has any idea how could you do that? There is a simple way to incorporate invariances, and it's just changing the representation. Instead of working with x, y, z coordinates in space, what you can do is use relative coordinates. These are called also internal coordinates, and it works as follows. Maybe you take this atom A and you place it at the origin, okay? So this is maybe placed at the origin, and now you say, oh, the atom B is going to be just a distance B away from the origin. I placed atom B in a position relative to the atom A. And now I'm going to have atom C that is going to be another distance here, and then atom D that is another distance. And then I'm going to specify some angles, maybe some angles between phi, between these vectors C and D, CD and BC. I specify this angle, and then I have this dihedral angle psi is the angle between the plane ABC and the plane BCD, okay? Just by using distances and angles, I have now internal coordinates, and they are invariant to rotations or translations, okay? Given these internal coordinates, I obtain my 3D spatial coordinates. If I translate or rotate the 3D spatial coordinates, the internal coordinates are the same. Okay? Good. So we are going to be using these internal coordinates to capture invariances. Good. How do you work now with angles? This is something, maybe this is a minor thing. Yeah, if you work with angles and you are constructing probability densities on angle variables, you have that an angle of 0 degrees is the same as an angle of 360 degrees. And you need to incorporate those invariances into your models. And it turns out that with the neural spline flows, you can do it very easily. In the neural spline flow, you want your density at 0, your density at 0, which is going to be given by the derivative of your transformation. Your density at 0, you want it to be the same as the density at 2 pi. So you are going to construct your spline function, your spline transformation, such that the gradient of your transformation at 0 and the gradient at 2 pi is the same. So when you have these spline functions here, imagine that this is 0, and this could be 2 pi. As an example, the gradient here and the gradient here has to be the same. And you can very easily incorporate that into splines, because splines are polynomials, and you can right away constrain the coefficients of these polynomials such that they have the right derivatives. Good. By doing that, you get now these densities. These are examples of densities that satisfy these invariances. This is symmetric. So the density, when you do this section here, the density at minus pi is the same as the density at pi. Okay? Good. It's the same as if you are defining a function on this kind of, what is going to happen is that you may have a spatial or variables that are not symmetric, like the distances. If you have a distance, the distance doesn't have any of these symmetry properties. But the angle has that property, and then you capture that by modeling your density in this manifold, which is just this type of cylinder. Okay? Good. You could have maybe 2 angles and some distance, and the manifold would be a torus instead of this cylinder, if you have 2 angles. Good. So that's how you capture invariances. Now, the next thing that you need to do is to eliminate bias in your model. We said that all these deep generative models, they are going to be biased because they are approximations to reality or approximations to your energy model. And then how can you eliminate bias? It turns out that there is a very simple way to eliminate bias in your samples. Imagine that you want to approximate an expectation with respect to your Boltzmann distribution of a quantity of interest given by this function. Okay? You can write this expectation as an integral of the function f with respect to your density p. Okay? But you cannot really work with p because you only know it up to a normalization constant, and this is a very complicated distribution, and you cannot integrate in high dimensions. What you are going to do is to draw approximate samples, and you're going to draw approximate samples from an approximate distribution Q that is not the same as P. But you want to get the right quantity. So what you can do is you can multiply and divide by Q in the original expression, and you have now this thing, the ratio between P and Q, that is called an importance sampling weight. And here now your, let's call this Wx. This is now the expectation with respect to Q of my function f of x, but now weighted. I am weighting my samples by this, not Q, sorry, Wx. Okay? So I am now weighting my samples by some weights. So I draw samples from Q. Q is not the same as P, but if I reweight my samples, with this density ratio between P and Q, I eliminate bias in my samples. You approximate the expectation by Monte Carlo, which is what we are doing here. We draw now n samples from Q, and then you just estimate your quantity of interest by averaging over the samples that you generated from Q, where you have reweighted your samples. Great, problem solved. No bias in your samples. Is that right? Or there could be some problem hidden here? Anyone can say something? What can go wrong here? Yes? Yeah, you have to sample the same support, but I don't know. Let's assume that you just work with Gaussians or transformations of Gaussians. They have support everywhere, and maybe your transformations are from everywhere to everywhere. So maybe that's fine. Is there any potential problem there?
Over here.
Huh? Yes?
You end up with really high variance in your estimate.
That's right. This is one of the limitations of this method called importance sampling. It can have high variance. And the reason it can have high variance is because these importance sampling weights, these weights here, the ratio between the two densities, sometimes they can be huge. And they're going to be huge because you are dividing by your sampling density Q. And imagine that maybe you have some distribution like this, P of X, and now you have a narrow approximate distribution Q. And sometimes you sample from Q and it might be fine, but once in a while you will draw a sample from Q in a tail, okay? And you may draw a sample from Q here, and what is going to happen is that the density of Q there is going to be extremely low, but the density of P is not. And then you are just, in your weight, you are dividing P over Q. Q is super close to 0, and P is large, and then you just get some massive weight there. And what can happen is that you draw your samples from Q, you compute your importance sampling weights, and one of the weights is massive, and the other ones are super small. You only have one sample then, given by the one with the massive weight. Imagine that you draw 1 million samples, and then one has massive weight and all the others tiny. Instead of 1 million samples, you only have one sample. And this is going to give you massive variance in your estimator, okay? There is still some good news. This estimator, or this way to remove bias in your samples, it can have massive variance. But it turns out there is a proposal distribution, a Q. There is a value of Q that is optimal. And it's a value of Q that is going to minimize the variance. In fact, it's going to give you an estimator with 0 variance. Okay? The optimal proposal distribution for importance sampling will have 0 variance. And it's as simple as follows. Your optimal Q could be just the product of whatever you want to integrate. Okay? So if you want to integrate F with respect to P, you could say that your optimal Q is going to be just the product of P and F, obviously normalized. So you're going to have a normalization constant there. And if you use this proposal, or this approximate distribution Q, and you do importance sampling, you have 0 variance in your estimator. And it's very easy to see. You just draw one sample. Even with just one sample, you just evaluate your the thing that you want to integrate. You have your importance sampling weight here is the density ratio between P and Q. Okay, this could be your importance sampling weight x1. And now you evaluate the function f x1. And it turns out that the ratio between f and P and Q optim, because Q optim is f times P already, is just the normalization constant of Q, which is what I want to estimate. This is what I wanted to estimate, is the integral of f with respect to P. So just one sample, and I get the exact answer. I only need my optimal importance sampling distribution. Obviously, my optimal importance sampling distribution sampling from it is as difficult as sampling from the original target, no? Like, because it's just the product of P. Sampling from P is difficult, so sampling from F times P is going to be also difficult, so forget about it. But yeah, why I'm telling you this? This is going to be important for the methods that I'm going to tell you about later. We are going to be optimal importance sampling distributions, and these are going to make a huge difference when we use these methods in practice. Okay? Good. Any questions on this? No? Good. So we can use importance sampling. Another limitation of importance sampling, I mean, we have said that you can have high variance, and imagine that you have something like this. Your proposal, it doesn't have mass in regions of interest. Then you are pretty, I mean, it doesn't matter what you do in this case. Your proposal is really bad. You are going to have high variance. You will never estimate accurately things. No? If you need samples in these regions, for example, my proposal Q is never really going to sample there. So I'm pretty screwed in that case. You can do something to improve importance sampling. And there is this method called annealed importance sampling, which is an amazing method. Annealed importance sampling was actually proposed by Radford Neal, which is also the first person that applied, that described this Hamiltonian Monte Carlo algorithm in the area of machine learning. And annealed importance sampling is going to allow us to obtain still unbiased estimators, but that are going to be able to generate samples even if our distribution Q doesn't have support in some regions. It has very low density in some regions. Annealed importance sampling is going to solve this problem. Okay? And the idea is that instead of just sampling from my proposal and then computing importance sampling weights, what we are going to do is to start sampling from this proposal. This would be my original Q here. Q of x is the same as pi 0. But I'm going to now draw samples also for intermediate distributions, where I construct these intermediate distributions that are combinations of the target P and my proposal Q. I get the intermediate distribution pi k, and they are just a combination of those with these coefficients that go from 0 to 1. So when the beta is 0, then I just have a Q. My intermediate distribution is just the Q. And when beta is 1, I get P. So I have now distributions that interpolate between P and Q. And instead of sampling just from Q and calculating importance sampling weights, what I'm going to do is to sample from all these intermediate distributions and calculate the importance sampling weights. So I sample from Q here initially, and I get a sample x0. And now I run Markov chain Monte Carlo to obtain a sample from pi 1, from the first intermediate distribution. Once I have this sample from pi 1, x1, I use it as an initialization to a Markov chain that samples from the next intermediate distribution, and so on, until at the end, I generate a sample from the target. What's going on here? What we are doing is just applying importance sampling, where I don't really target P directly. What I'm going to be targeting with importance sampling is all these intermediate distributions. And then, by doing that, you can actually reduce variance in importance sampling. We have also, so imagine that you do this and you get this final sample xk that is going to approximately target, it's going to be an approximate sample from the target. Pi k, this is the same as P of x. Okay? And we can calculate importance sampling weights for all these distributions. So I start by sampling from Q, and I want my sample from Q to be a sample from the first intermediate distribution. So I calculate its importance sampling weight, and now x0, when I weight it by this importance sampling weight, is an exact sample from pi 1. No? I'm computing the importance sampling weight for the first intermediate distribution. Is just the ratio between the first intermediate distribution, pi1, and my sampling distribution, pi0. So x0, when I reweight it by this, is a sample from pi1. And what I'm doing now is I run Markov chain Monte Carlo, initialized with x0 and targeting pi1. Markov chain Monte Carlo, this is another sampler. This could be Hamilton Monte Carlo. It receives as input x0 and it generates x1 as output. Hamilton Monte Carlo is going to preserve the target distribution pi1. So I have x0, I reweight the sample to be an unbiased sample from pi1, and then I run Hamilton Monte Carlo targeting pi1. And now x1, the output of Hamilton Monte Carlo, is an unbiased sample from pi1. And I now reweight it to be an unbiased sample from pi2 by computing this density ratio between pi2 and pi1. And now x1 is going to be an unbiased sample from pi2. And I just run Hamilton Monte Carlo, preserving pi2, and I continue. And in the end, I get this reweighted sample, xk, that is an unbiased sample from the target. Okay? But I generated this unbiased sample from the target using intermediate Markov chain Monte Carlo steps. And this is going to reduce variance massively. And it's going to solve the problem that I don't sample from regions where I don't have mass. So imagine that your target here is this mixture of two Gaussians in blue. This is your target. And your proposal is this Gaussian in the center in green. Horrible proposal. You don't have mass covering the target. Okay? If you do important sampling, you have massive variance. Most of your samples have 0 weight except those ones in the tails here. Okay? These are samples that I get in the tails of my green distribution. They are the ones contributing to my to my expectation. But I don't have many samples there. If you run an important sampling with all these intermediate distributions, the final samples that you get, they are covering the target. Okay? So even if my initial proposal didn't have mass there, I am improving those samples quite a lot, and I am getting unbiased samples with corresponding important sampling weights. Okay? And you can see the distribution of the important sampling weights. Here is very flat. You have massive variance on the important sampling weights. And here the variance of the important sampling weights is much smaller. Okay? You can show that an important sampling will reduce variance in your important sampling weights. Good. So I'm already done. Now we are going to use this method to remove bias in the samples from our method. So now, how we train our models? We said that we are going to train them from energy and not from data. And to train them from energy, we need to minimize an objective that will depend on the energy. And one thing that you could do is minimize this Kullback-Leibler divergence. Probably you have seen this many times in machine learning. It's called variational inference. You just minimize this Kullback-Leibler divergence between your approximation Q and the target. And the good thing is that this only depends on the logarithm of the target, and it's independent of normalization constants, so you could just use it right away in this case. Great. The only problem is that this doesn't work in practice. So if you try to fit your generative model to one of these Boltzmann distributions, minimizing this divergence, you are going to miss many modes in the target. So this is the samples from your model when you minimize this Kullback-Leibler divergence, and the target is this multimodal distribution shown with contours here. You miss many modes. And the reason for this is that this Kullback-Leibler divergence is mode seeking. And it will focus on regions where you cover modes. The main reason is that this log density ratio here, it represents the error. When Q and P are the same, the ratio is 0. Is 1, the log of 1 is 0, so there is no error, and the divergence is 0. And when P and Q are going to be different, you will have high differences. But this error is weighted by Q. So in regions where Q has low density, you don't care about the error. So if you are not covering a mode here, If you don't have density, your approximation Q has no density there, you don't care about the errors. So this makes this method miss modes, and that's not going to be good in practice. So what we do in this work is to minimize a different divergence that is not mode seeking, that like the Kullback library divergence, but is mass covering. And you can obtain it by using this alpha divergence. It has this fancy mathematical formula. It's just similar to the Kullback library divergence, but it has this extra parameter alpha. And when you have alpha equal to 0, this is the same as the Kullback library divergence. It's mode seeking. If you are approximating P, which is multimodal, with Gaussian, which is unimodal, you tend to cover only one mode. But as you increase alpha here, you make alpha larger, you move into mass covering solutions that try to cover all the different modes. And instead of using alpha equal to 0, which is the Kullback library divergence, and it's mode seeking, we are going to use alpha equal to 2, which is going to be mass covering, and it's going to allow us to cover the different modes. There is also another advantage of using this alpha divergence with alpha equal to 2. You can show that the alpha divergence with alpha equal to 2 is the same as the expectation of the square of the importance sampling weights, and this is related to the variance of the importance sampling weights. So if you minimize the variance of your importance sampling weights when you have an approximation Q, you are minimizing this alpha divergence, and you are guaranteed to be mass covering. This is the objective that we are going to minimize. We are going to have now normalizing flows that optimally fit the target in a way that when you do importance sampling to remove bias in your samples, you have the lowest possible variance. And that's going to be great to eliminate bias, obviously. So the question is, how do you minimize this alpha divergence with alpha equal to 2 in practice? And we do it very efficiently by using importance sampling. You need to estimate the objective. The alpha divergence is this integral. It's a complicated integral with respect to these functions. It's intractable, but you can estimate it with importance sampling. And you can use an optimal importance sampling distribution, which is just whatever you are integrating. No? We saw that the optimal importance sampling distribution is just proportional to whatever you are integrating, and here you are integrating P squared over Q. So our optimal importance sampling distribution to estimate the alpha divergence is just proportional to P squared over Q. And what we are going to do is to, instead of use samples from Q to estimate the alpha divergence, you could estimate this with a importance sampling using samples from Q. So this is going to be the integral of P squared divided by Q. And then if I am integrating with respect to Q, I need to divide by Q again. So I could use importance sampling with samples from Q, and now I compute the P squared over Q squared. This is how I would be estimating this with samples from Q. You just draw samples from Q, then you average over those samples P squared over Q squared. Okay? And that would be your importance sampling estimator of the alpha divergence with samples from Q. If you do that, that's not going to work. You're going to have massive variance in the estimation of the alpha divergence. What we do in practice is we are going to be using samples from this optimal importance sampling distribution. And the amazing thing is that you can show the gradient of the alpha divergence. And if you have optimal samples from P squared over Q, which is this thing G, this is just P squared over Q, the gradients are the same as the maximum likelihood gradients. If you want to maximize the likelihood of Q on samples from P squared over Q, that's going to give you the gradients to minimize the alpha divergence. So the way to minimize the alpha divergence is you draw samples from P squared over Q, and you fit your flow by maximum likelihood following the gradients of the likelihood on those samples from P squared over Q. And you can imagine that when Q is the same as P, P squared over Q is P. So then you are just fitting your model by maximum likelihood to samples from the target. Anyway, you can show that doing this gives you massive reduction in variance when you use this objective. And the idea is that you are not fitting your flow to samples of the target or anything like that. If you have a target like this in orange, P, it would be this curve here in orange. You don't fit the flow to samples from this target. If you have this approximation Q in blue, now you maybe you want to update the parameters of Q so that you fit the target more. And what you do is you sample from this distribution P squared over Q, which is this one in green. And it's sampling from those regions where you are missing mass in your approximation. This part on the left is where the orange curve has high mass and the blue one has low. So you don't really sample from the orange curve, you just sample from this one in green that is more to the left, and it's going to move your distribution faster to cover missing regions. Good. I won't go much into the details, but this gives you massive reduction in variance. So this is the signal to noise ratio in the gradients of the alpha divergence, and in red you have our method, which is much higher than even doing important sampling with the optimal distribution. So even if you had optimal samples from the target P, and you wanted to estimate this alpha divergence by that, the alpha divergence is proportional to P squared of X divided by Q. So you could approximate this with samples from P, and you just need to estimate the ratio between P and Q. So it would be an expectation of this. If you do that with samples from P, it's bad. It's even bad than what we are doing here. The question is, how do you get the samples from P squared over Q? And we do it using an yield importance sampling, just targeting P squared over Q. So the whole process is as follows. You have your target P, you have your approximation Q. What you do is you use an yield importance sampling to obtain approximate samples from P squared over Q. You have unbiased samples from that distribution because you get important sampling weights, and you just follow the gradient of the likelihood for your model on those samples. It's just that. I'm going to skip this because I'm a bit short on time, but the idea is that we draw samples from P squared over Q with an yield importance sampling and use those to update the flow by maximum likelihood, but we don't throw those samples away, because it would be wasteful. We keep them in a buffer, and we sample samples from the buffer with probability proportional to the importance sampling weights. And this gives you like a buffer of data, and you just sample from this buffer very fast. So how does this work in practice? You have a flow initialized like this, trying to fit the target, which has tons of modes. This is what you would obtain with a flow. The samples of a flow fit by maximum likelihood. You cover all the modes because you are training on data from the target. But normally you don't have data from the target. Okay? If you train a flow by minimizing the Kullback-Leibler divergence, you miss many modes. And this is basically our flow trained with this buffer that is basically the same as maximum likelihood. But we don't have samples from the target here. This is a toy problem. We tried it also modeling this molecule, alanine dipeptide. This is a common benchmark in the modeling of molecules. It's a simple molecule like this, but it's more or less rigid in most of the locations of the atoms except for these angles. These are angles between specifying the 3D configuration of the molecule, and they are the ones where things can vary more. And you see here a ground truth histogram of the density for the values of those two angles. And you see that you have several modes. The density is symmetric. Minus pi and pi are the same here, and the same for the other angle. If you fit a flow by maximum likelihood on ground truth samples generated with molecular dynamic simulations with Markovskian Monte Carlo techniques, you will get samples like this, and your model is sampling in this region where you don't have much data. You didn't have much data there, you don't really know much what is the density of your model, and it's just generating some values in that region. This is what our flow generates. It's obviously biased, but we can eliminate bias now by reweighting the samples. And when you eliminate the bias, the samples that you obtain are almost perfect. They are indistinguishable from the ground truth ones. So these samples here on the right, they are almost the same as, they're indistinguishable from the ground truth ones. You can look at a one-dimensional histogram for this angle, and you can see that we capture very well. Our method reweighted is this one in pink, and the ground truth is in black. And you can see that we capture these regions quite accurately, and we capture all the modes as well. We compare also with other metrics. We look at the effective sample size. The effective sample size, it measures how many effective samples you have when you do importance sampling. If you have a massive weight in one sample, your effective sample size is just one sample. Okay? And if all the weights are uniform, your effective sample size will be the number of samples that you have. Here, effective sample size is measured as a percentage of the samples that you generate, and our effective sample size is 92%, which is super high, because we have very low variance in our importance sampling weights. And you have see here a flow trained by maximum likelihood on ground truth data, and the effective sample size is still very low, because that flow was just trained by maximum likelihood, not to minimize variance in importance sampling weights. So just to conclude some messages here, I have described this method that we call flow and yield importance sampling bootstrap. It allows you to fit these multimodal distributions. It's trained from energy values only, and it combines this alpha divergence and yield importance sampling, bootstrap training, where you sample from your flow using, you sample from the flow, you improve the samples using an yield importance sampling targeting p²/q, and then you refit the flow on those samples. You only require the target and not samples, and we got state-of-the-art results on this dipeptide. Previously, all the models, they would have like huge biases when you sample from this dipeptide, and our model had almost no bias at all. So now, just to conclude, I want to give you some reminder of the challenges in this area, that you need to train from energies and not samples. You need to encode invariances. You want to cover different modes. You want to remove bias in your models. You want to scale to high dimensions. In these problems that I mentioned, we are only working on small molecules, but we are now working also on higher dimensional settings using other models. You want also to generalize across molecular systems. If you train your flow on a particular molecule, maybe you want it to work on other molecules. And just to conclude, I can give you some news. With some students, we have created a startup now that is working in this area. It's called Angstrom AI. We co-founded this recently. It's only 2 months old, and we are working on this technology, especially working on diffusion models. I said that diffusion models have many limitations if you want to apply them in this setting. We're actually solving the problems of diffusion models, and we plan to have very exciting technology very soon. And that's all. Thanks a lot, and if you have any questions, I'm happy to address those.